Actually, it's a big pleasure presenting again on Hackers to Hackers conference. And actually, I opening after keynote the talks track. And my talk will be about BIOS vulnerabilities. And actually, we will talk about a lot of different things, include Intel Boot Guard and Intel BIOS Guard. And I will introduce myself a bit. So I embedded security researcher, have a lot of experience in reverse engineering, and actually before of that I been working for Intel, ESET and Cylance, and also co-authoring the book Rootkits and Bootkits, Reverse Engineering Next Generation Threats. So today we will start about the attacks on the BIOS updates, and then continue with some new vectors of bypassing and attacking Intel Boot Guard. And also we will talk about architectural things Intel BIOS Guard, which is actually very hidden. It's not actually, don't have any public information about architectural things of Intel BIOS Guard from Intel. Also, I want to actually promote two talks, which is one of them, it will be 3 p.m. today from Alex Yermolov. He will be talking about BIOS vulnerabilities too, and also he will cover some things about debugging, hardware debugging with DCI interface, which is very interesting and very useful for vulnerability research. And other talk will be happens tomorrow. It's Alex Bazhanyuk. He will be cover the vulnerabilities from SMI handlers and also trust zone. Let's start a bit with introduction. And if we look in the history perspective how rootkit's been involved, and in the beginning it's been delivered by some dropper from user mod in ring tree, and actually dropper loaded the driver, and after that when Microsoft introduced starting from Windows 7 Microsoft sign-in policy, it's a bit moved to bootkit's world when we do have like infections for MBR, VBR, and where the loader actually going to modify Microsoft bootloaders and then load some malicious component to kernel mod directly. So, and if we focus it in nowadays, after secure boot is coming, so could you open please? So after secure boot being is appeared from Windows 8, so it's actually very difficult to find the machine where the secure boot is not active. So actually nowadays, the rootkits start moving to closer to hardware, and actually specifically to SMM, which is a system management mode. And system management mode, it's very interesting from the attacker perspective, because you have a power to have access all the physical memory space, and also you can actually discover all the memory which is responsible for kernel mode, for user mode, even for the virtualization stuff. And if we look into the state-sponsored attacks, which has been disclosed with the WikiLeaks and Vault 7 and other things, actually, usually it's like that. We have a trampoline, which is into SMM, and then the loader getting into operating system level, which is actually load some component inside kernel mode, because actually it's much easier to track application from that level. If you want to intercept some messages, whatever, of course you can parse all the memory from SMM, but it's much complex than just use the rootkit inside the kernel mode. And more mitigations, actually more rootkits complexity, and what we can see is now in nowadays, the rootkits moving to closer and closer to the hardware, and actually we have a lot of information already on the public about the BIOS implants, and it's like not a myth, it's really true, but it's complex and it's actually expensive to develop, why it's using for state-sponsored attacks and complex APTs. I need some water because yesterday been a party. And actually, modern rootkits move into hardware closer. And if we actually look at this picture, it's copied from presentation from Rodrigo Branco and Vincent Zimmer from Black Hat this year. And they actually disclosing some vulnerabilities from which is being processed by Intel PCert. And we can see the growth of configuration-based vulnerabilities, which is actually says like we have the platform which is being configured not a proper way and has vulnerabilities by default on this hardware or BIOS configuration, whatever, which is specifically says it's very useful for attacker. And today we will be actually discuss some of the vendors which is has a lot of problems with their hardware. From other perspective, we do have a lot of attention from the big companies like Google, Amazon, Microsoft, because they do have a cloud, which is actually has a hardware. And as example, if one of these servers have a BIOS implant, this BIOS implant can discover like all the guests on this server, and for the cloud attack, it's like extremely dangerous. And recently, Google been introduced the Titan chip, which is protects the root of trust from the hardware. And as example, if you have a server with a Titan chip, it will be armored the BIOS updates and also make some attestation for the hardware inside the platform, which is very interesting, and it shows like modern way how the big companies moving to develop their own hardware for protect from supply chain attacks. But let's move to the BIOS updates issues. And it's very interesting because actually last year I already discussed the problems with the BIOS updates, but this year I discovered more. So UEFI world is huge, right? So we have automotive, we have like a lot of different platforms which is used UEFI, even like IoT space sometimes use it. And we have like huge ecosystem with the different vendors, which is like use different SDKs, frameworks. As example, we have Intel EDK 2, but also like on top of it, we have American Megatrends, Phoenix, Insight, which has produced some of interesting frameworks for vulnerability research. And now actually, if we talk about the legacy BIOS is gone. Actually, UEFI is everywhere, but now legacy inside the UEFI, because it's very complex. We have a lot of different components. It's very difficult to keep all the things up to date. And look inside the BIOS update image, how many different firmwares we have for just one UEFI image for the BIOS update. It's more than 10 different firmwares for different hardware components into your motherboard. So we do have like different sensors, graphics, networks, ME, BMC, AMT, actually microcode, BIOS guard, and TXT. So today we will focus more like on BIOS guard, boot guard, and ACMs, a bit touch the management mode, and of course we will be discuss some vulnerabilities which I found for this talk. And here is 4 different vendors involved, actually 5. So American Megatrends, but American Megatrends produce some framework which is used by Gigabyte, Asus, Lenovo, and MSI, and I found vulnerabilities specifically on these vendors. So let's talk a bit what kind of protections do we have for the BIOS. And if we look on the left side, we have some simple bit protections, which is actually easy to bypass and easy to forget for enabled, which is actually a lot of vendors does. And here's the issues which I found. Other ways we have PRX registers, which is kind of policy for access for spy flash regions, and it's actually separated from BIOS protections bit, which is makes sense, and if both enable it, it's much harder to bypass it. But it's also like we have a vendors which is don't use it at all. From other thing, we have a like sign-in and authentication for the updates, and also like not all of vendors use it. And of course, fancy technologies like BootGuard and BIOSGuard. And we also today will discuss two issues which I found for my Black Hat talk. And look on this picture, actually the spreadsheet, which shows how different vendors use these simple protections. And if you look on top, which is actually highlighted by red, you see like ASUS, MSI, and Gigabyte, they just don't care. So it's like simple things doesn't used, even like BIOS updates, it's not authenticated properly. So they just don't care. And for my talk in Black Hat Asia this year, I'm already actually demonstrate how it can be dangerous with a simple demonstration and proof of concept of UEFI ransomware. You can find by this link this material. So, and this actually demo being demonstrated from Office document to SMM. So, and it can be used for remote attacks, and it's actually already probably used. And I have a questions to audience, actually. Do you update your BIOS? Who never update your BIOS? Okay, who update just once? Yeah, so actually, thing is like, usually it's very common. Normal users never update the BIOS. They just bought the hardware and that's it, because they actually didn't know they need to update the BIOS, right? It's not delivered with a Microsoft update, how they usually actually Microsoft does patch on Tuesdays. And everybody forget about this, and it's extremely vulnerable thing, and keep be vulnerable even with already patched issues like years. Sometimes like all the life of your laptop, it can be vulnerable. So, and if we back to proof of concept of UEFI ransomware, I used these issues for bypassing the BIOS update authentication, and actually it's been few stages, and one of them it's been exploiting SMI flash SMI handler and make a privilege escalation to SMM. And also interesting thing, actually, American Megatrends has a driver, kernel mode driver, which is signed, but this driver actually, user mode application tell to this driver which kind of SMI handler should be called. And this driver can call any arbitrary SMI handler. So, and actually I use it for attack SMI flash for my demo. So in generic way, if you look to this picture, we do have different stages how the BIOS update can be delivered. On first stage, of course, it's update application, which is running on user mode. Then it's loaded some driver, which is made BIOS update image to the memory, and then like update image being catched by some of the SMI handler, which is responsible for the BIOS update process. And we actually do have like two of them, SMI flash and security SMI flash. And most interesting part, I also found the issue with security SMI flash. And security SMI flash responsible for validating the signed update. So if you found the issue with security SMI flash, you can just bypass all authentication, because you actually already escalate the privileges in this driver, and you can modify flow in runtime, which is funny, right? So SMI flash does have this kind of SMI handler, which is write, read, and erase. and highlighted by red, it's been vulnerable for different platforms which I found for this research. The interesting thing, it's very easy actually to fix this kind of issues with a security check, but I don't know, BIOS developers too lazy. Same thing about security semi-flash. We do have 3 semi-handlers, and in my case, it's been all of them vulnerable. Actually, it's specifically why the BIOS guard and boot guard been created, because they want to protect from the SMM issues, the BIOS update and armoring, not only BIOS update, even like secure boot from before the SMM and BIOS will be loaded. So a bit about the responsible disclosure, and it's kind of fun, right? So I do have communicate with different vendors, and actually it's been good response from Lenovo, and Gigabyte been a bit slow, but they at least patch it. But the ASUS been best. So I submit the issues to them, and after a month they say, so it's no issues, no issues. And I actually download the recent update for the same platform where I found the issues, and they actually silently released the patch with my issues. So I make simple bin diff and discover where they patched the issues. It's been my issues. So I make it this tweet. It's been some support from community. And actually, after that, they send me email. Sorry, we actually not mention you, but yes, it's your issues. That's kind of cool, right? So it's ASUS. Let's focus more interesting and serious things like Intel BootGuard, and why actually BootGuard been created. So the main thing for BootGuard is armoring the secure boot flow, and if we're talking about the secure boot, so it's been there like since 2012, and almost every time it's been based on root of trust, based on BIOS. So, and attack surface, it's all the firmware, right? So then in 2013, it's been introduced the BootGuard technology, which is armored secure boot flow. And it has 2 options, like measured boot and verified boot. So measured boot, it's more software mode, which is like use the TPM as a root of trust. And here is the same problem. It can be attack surface based on the firmware. And verified boot is most strongest mode, where actually root of trust moved from the firmware to the hardware and locked by one-time programming field fuse. Yeah, and actually we will discuss some of bypasses for this technology today, not only mine, and it's very interesting. And so actually, why is this technology being created by Intel? Because classical secure boot start the flow from the Dixie phase, which is actually last phase before it's passing control to the bootloaders for operating system. And here's a lot of issues with implants and bootkits from SMM for that. And actually, classical secure boot been for like a UEFI, it's been created for validating and authentication bootloaders for operating system. But then it's kind of difficult because all the issues from SMM can bypass it. And it's no verification for most early boot stages like sec stage, security stage, and platform initialization stage. And on other actually side, we do have a measured boot, but same thing. It started earlier than Dixie, but also can be bypassed from the firmware. And only actually verified boot can be more interesting mode for protection, which is like moved root of trust to the hardware. I'm already actually showed in my previous year presentation this picture. It's from the Vincent Zimmer's blog, and it describes how Intel BootGuard technology works. It's not a lot of details, right? So most interesting thing, it's kind of root of trust going to the hardware. And I reconstructed this picture from different sources based on presentations from the researchers and the books, which is available on public, but it's not yet Intel released the specification for that technology. And we can see, so actually, we do have a microcode, and which is authenticate ACM for the boot guard, and only after that it's passing control after verification to reset vector, and a reset vector actually loads initial boot block, which is IBB, for check the second phase stage and passing control to the secure boot on the Dixie phase, and then verifies the OS bootloaders, which makes sense. And BootGuard has a three operation modes, which is like not enable it, measure it, verified boot, and verified boot plus measured boot, which is most strongest mode. Here's a picture from one of the Intel papers from IDF. I don't remember which year, probably 15, right? So, we can see how the actually root of trust and policies going from the Intel BootGuard and passing each level to the next one. And the thing is, like, it's not really showing anything. You can see, like, okay, we do have a policies with checking some different phases, but what actually the technology does. And the root of trust, it's fuse programmable, one-time field programmable fuse. And actually, start pay block, it is an initial boot block, IBB, in terms of BootGuard technology. And this policy is checked by ACM. And let's look on more detailed picture. So we do have a part which is based on hardware, and we have management engine, which has read-write access to field programmable fuse, which is actually stores a hash, OM public key hash, which is actually a root of trust for other firmware image policies. So we do have in BIOS update K-manifest, which is store like a lot of different things, and initial boot block manifest. The interesting thing, like this chain have like chain verification policies, which is locked in hardware. Thing is, field programmable fuse, it's very sensitive place, right? If it's not locked, it can be an issue, but we will be discussed a bit later about that. And other thing, for any modification of FPF, we need access, read and write from the management engine to these regions. Just before my Black Hat talk, Dell released the paper, here is a link, about how their implementation of BootGuard works. And it's pretty interesting because it has much more details than Intel ones. And here is actually, we can see like PCH responsible for the fuses, and it's why actually ME is involved. And inside the BIOS updates, we have these structures, which is similar stuff, but in different visualization, which is I just discussed. And if you're interested about the BootGuard technology, I highly recommend to look this link. But same thing, like what is what, right? So here is specifically FPF and all of this stuff stored in BIOS update image. I checked security for different platforms. And if you think actually Apple's the best ones, it is not. Because we have Apple right there, and it doesn't support bootguard, it doesn't support a lot of different things, and actually secure boot is not the securest one for current state at Apple platforms. And but worst one is actually Gigabyte Bricks, because it's too much power and flexibility for the attacker exists here. So we do have like read-write access to the memory regions. We do have read-write access to the embedded controller. We do have DCI CPU debugging enabled. It will be discussed a bit more detailed from Alex Yermolov talk at 3 p.m. today, why it's actually so dangerous. And other stuff, we do have like FPF not set, and bootguard FPF, it's not programmed. So it's kind of interesting, and we will be focused a bit more on it. And BIOS guard is disabled, so it's perfect target, right? And also I want to highlight actually the Dell and HP did a good job, so they actually most securest one from my research. So if you think hardware vendors care about security, it is not. Not all of them really cares. The first thing, as example, small vendors like Gigabyte, Asus, MSI, they even don't have a security teams, which has been like, will be like checking the security for the hardware, which will be released on public. No, they don't have. Even more, if you submit the issues to them, it's very hard to like prove it is an issue, because they not understand a lot of things from the security research space. So trust no one. And also I want to make some reference to initial research which has been did from, which has actually been done from Alex Yermolov, and here is a link. He first who found the issue when BIOS bootguard being not enabled and also programmable fuse not been locked. That means like attacker can use bootguard for lock the rootkit inside the platform. Yeah, but attacker actually never attacks specification, right? So it's always focused on implementation stuff. So, the thing is, let's talk about how the bootguard is implemented. And if we do have this stuff inside the BIOS update image, and the fuse, it's not set, we only rely on the firmware security. And even if you have verified boot active, it doesn't matter. The configuration doesn't locked. So I recovered the structures for the K manifest. It's not documented, and it's my templates from 01 editor. So we can see what it is. We do have IBBM hash, which is a vendor hash, RSA OM public key, and RSA signature. So, and also the IBBM public key, which is plus K manifest security version number. On the other side, we do have initial boot block manifest, which is a bit complex. And the main thing, it's actually has the hashes and offsets for initial boot block for protecting most early stages of booting, like pay and sex stage. And actually, if you look into UEFI tool, which is a public tool, and you can download from the GitHub, it already has found found the BIOS guard ACM and boot guard policy and boot guard K manifest, and you can easily dump from them. It's because like Intel has this kind of fit entry technology, which is offset based, and it's documented in EDK2. And actually, let's look inside the boot block, how it looks like inside the policy. So we do have hashes and offsets, which is actually pointing us inside the BIOS image what kind of region is protected. We have a beginning and the end. And specifically for my attacked platform, we do have the coverage, which is started mostly from the beginning of the firmware image and covered all the sec and pay and Dixie phases. And also very interesting part is ACM, which is authenticated code model, because it's actually not a lot of information on public how this kind of code is executed. And specifically on Intel platforms, and actually I didn't see any ACMs which has been not developed by Intel. And BootGuard ACM is verified by microcode. So the microcode checks the digital sign for authenticated model. After that, it's loaded to the cache with non-invicted mode and executed. So we do have entry point, ACM header, and also RSA public key. Exponent is stored here, and also RSA signature. A very interesting part, sometimes IBB, initial boot block, doesn't cover all ACM model and cover only the header. And thing is, like, if it covers the header, it's very like difficult to modify anything, right? So because microcode, based on this header information and information which is stored inside, check the signature, and if anything is modified, the ACM code will be not executed. But also, thing is, like, we know the entry point, right? So we know how the code and where it starts. A bit information about ACM. So ACM for the boot guard, it verifies K manifest and IBB, and also it's executed in ACRAM, which is a cache as RAM. And I developed a loader for IDA for loading ACMs and make the research for ACMs more handy. So it's a flow from ACM, and it's verification flow from the entry point. We can see, like, it's checking the boot guard policies, and also this graph actually demonstrate how many basic blocks we do have inside the ACM and how complex it is. So it's a bit bigger picture. From the entry point, we have a boot guard validation, platform init, and actually we're getting some manifest from the firmware image, which says clearly we do have parsers inside ACMs. And after I think about parsers, always I think about the bin diffing from the past version of ACMs. And I did actually some bin diffing for different versions of ACMs. As example, I compare Haswell and Skylake. And here is actually not a lot of changes, just one. But when I make it from Broadwell to Skylake, I found a lot. And mostly it's been exist inside different parsers, routines, and some of them actually patch integers, overflow, and others. And it's kind of interesting because ACM, it's loaded on the beginning, but it still keep it in the same offset where it's been loaded on the beginning into the memory, and you can find it. And so if you know some issues and you know like BIOS is not updated, you can actually exploit some of the issues inside ACM, or probably you can do something with that. So inside the firmware, we do have following components for bootguard, which is responsible for different things, and most actually interesting things, actually all of them, because it's different stages of verification. And here is my reconstructed flow on pseudo C language. So, and here is actually verification for IBB from bootguard PA, platform initialization driver. And what it actually validates, it validates, of course, offsets and also platform hash key, which is I reconstructed from the gigabyte update, where we're looking for now. And we already actually seen this coverage for IBB, for specific BIOS update. Here is a bit information how actually from SMM we validate the flow, and we do have different things. The most interesting things actually, SMM driver communicates with ME management engine over HECI driver, which is very interesting because if we do have any issues with ME, that means we can actually operating in the same way, but from the operating system level, like from the kernel mode. So, and what actually verify firmware bootguard driver does? It does actually a few interesting things. It's find and verify ACM, verify K-manifest, and verify boot policies, but it's do it from the SMM. That's mean like we do have the state when not all of the boot flow for verification is involved, right? And I start thinking about how actually different flows for the boot and reboot the platform is worked, and then I'm figuring out, so for the sleep mode, it's not verified all the flow, and actually it's just verified some part of it. And specifically for the black hat, I dropped this 0-day bug, and thing is like already patched for a lot of platforms, but it was funny. After my talk, some of the vendors comes and says like, wow, we just actually last week patched this issue, and it's been cool because it's been best confirmation the bug is existing in real platforms and hardwares, not only the shit gigabyte. And after a while, after 2 months, actually, Intel patched for Intel NUCs, and kudos to Alex, he is found for Intel NUCs bootguard bypass based on my discoveries before, and he published very detailed blog post about it. So in my case, in being target platform based on Gigabyte, it's 6th generation Skylake with fully enabled Intel bootguard, but not logged by hardware. And BIOS guard, it's not enabled, which is make it much more easier to bypass. And I found 2 vulnerabilities which is used for this bootguard bypass. First of one, it's a read and write access to EMI regions. Other one, the fuse it's not locked. So we just showing it is true from EMI info tool. So you can see like EMI access for read and write is enabled, and bootguard is enabled. And actually, bootguard is enabled with most strongest mode, like verify it and measure it boot together, but it's not locked for the vendor hash key. So, And also funny part, Gigabyte specifically for this platform says like, it's very secure. It can be used in ATMs, in like critical infrastructure, vending machine, security system, governmental hospitals, whatever. And the same platform I actually used for POC of ransomware. How we can bypass this platform with a boot guard? So we do have firmware update image which is not properly authenticated, and we do have like initial boot block which is we can modify because like the configuration is doesn't locked. So we can modify K manifest, we can modify vendor hash key, OEM hash key inside the firmware programming fuse, and then we can log with a rootkit or just disable it, whatever. It will be not enabled and will be allow us to bypass the secure boot from SMM and don't care about the boot guard. So if we don't have the root of trust into the hardware, that's actually means it's very, not very easy, but it's possible to bypass from the firmware. Doesn't matter. It's like you use verified boot plus measured boot. Doesn't matter. It can be bypassed. So here's the Intel statement, which is actually Intel PCert sent to me before my presentations, and they provide some requirements to the hardware vendors, and they clearly say to them like the root of trust should be locked inside the hardware, but not a lot of hardware vendors really cares, right? And here is actually a Gigabyte statement about the issue. So they release a tool which can be lock the fuse, but how many users will really download this tool and use it for lock the fuse, right? I think it's like really small numbers. And it's small update for this presentation. Just a few days ago, I released an update for UEFI tool, which is made a verification for boot guard and showing the problems if IBB doesn't cover some of the models which can be used for attack. Here's actually a GitHub link to specific release, and here is compiled binary. If you don't trust this compiled binary, just compile yourself from the GitHub, from the source code. And here is a blog post which is discussed all the things and how this tool can be used. And let's talk a bit about the BIOS guard. So BIOS guard, and why it's important actually to have the BIOS guard and boot guard together enabled on the same hardware. So actually BIOS guard, it's armoring the BIOS update routine. So, and if the BIOS guard is enabled, access controlled by ECMs, BIOS guard ACM, and actually BIOS update authenticated from microcode. So it's a picture from Intel documentation, which is also doesn't say a lot. And I looked in specific implementation from American Megatrends, where I discovered how many things responsible for the BIOS guard we do have into the firmware. And here is like 7 different drivers, UEFI drivers, exist on different stages, phases of booting. And it's actually a huge attack surface, which is will be a bit more detailed, discussed in the Zero Nights talk in the next 3 weeks. So, and here is some details what this kind of modulus does. And we also see like things like update image parser for recovery process. We do have like BIOS guard policy override module. We do have capsule update verification, which is also pretty like complex parser inside. And we do have SMI handlers here, right? So BIOS guard has like commands for like different stages, like platform initialization, and for SMM for delivering the updates. And more details I will talk about on Zero Nights. And I want to actually promote the Hack Quest, which is kind of CTF for individuals, which will be started next Monday. Here is the links, and if you want to compete with the Russian hackers, go here and try to get some prizes. So come to Zero Nights to hear more details about the BIOS guard. And here is the link with the presentation and all the stuff about this research. Thank you very much for your attention. And do you have any questions? Anyway, if you not have it now, I will be around during the conference, and come to me to discuss more issues about the firmware or whatever. So here's my Twitter. And thank you very much again.